So here we have a vector space of functions which are polynomials of degree 3 and below. And I don't think I spent time showing that such a space is a vector space, but we'll just accept that it is. The vector space, any vector space has to have two operations. What are those?
Vector
addition
and multiplication.
Yeah, and scalar multiplication.
Scalar.
Right? Vector addition and scalar multiplication. Those are the two operations, and you have to show that those operations satisfy a list of properties, and I listed 8, right? So showing that something is a vector space is kind of long and tedious, which I don't plan to ask you to do. Rather, this is somewhat simpler. So I can give you a subset of a given vector space. So here P3 is the polynomials of degree 3 and below, and you pick a polynomial, and if that polynomial has a property that evaluation at 1 plus the derivative at 1 adds up to 0, we say it belongs to U. Okay? It's certainly a subset of P3. Right? P3 is a big set. It's an infinite set. Any vector space other than the trivial set is an infinite set. Right? But then if you have this subset, then how do you know that a given subset is a vector space as well? That's the problem. Okay? That's what we want to show. And when you already have a subset of a bigger vector space, then things are drastically simplified because the two given operations are already satisfying the lists of properties that you want, right? The vector operations, vector addition among two polynomials. Adding two polynomials gives you another polynomial. You can multiply a number to a polynomial, it's again a polynomial. Those we're assuming that somebody already showed that it's a vector space, meaning that those already satisfy the properties, right? So when you have such a thing, you just have to show a few things. You just need to show that U is closed under addition, and it's closed under any scalar multiplication. And if you show those two things, then everything else will follow. So, for example, one of the properties for a vector space is that any vector should have the additive inverse, right? But if you have scalar multiplication, taking a polynomial and multiplying it by -1 gives you the additive inverse. Right? Now, of course, you should also make sure that this set is not an empty space. Empty spaces are not called a vector space, okay? So you have to show that at least there's one element in the vector space. Yeah, to show that it's not an empty space, I guess it's good to show that 0 is included. All right, so let's do it in 3 steps. So proof, if P of x is 0, then P of 1 is 0, and P prime of 1 is 0, so this is a 0, almost trivially, right? So 0 is included in U. Now, at first I thought you don't have to show this, but I realized that this condition is there just so that you know that the space is non-empty. Okay? So we know that there's at least something in here. Okay, now, so that's the first thing that you want to show. And then second, so number 1. Number 2, if P of x and Q of x are both from U, okay, so we have two polynomials from U. Okay. So that P of 1 plus P prime of 1 would equal to what? 0, right? Being in U means that's true, right? How about Q of 1 plus Q prime of 1?
0.
Again, 0. Being in U means that's true. And now I want to show that px plus qx is still in U. So what I'm going to do is I'm going to define h of x as another function defined as px plus qx. Okay, so we have px plus qx. This is going to be our new function. And want to show that this is in U. Okay, how do you do that? So we say let hx be the sum of the two vectors. These are polynomials, but it's a vector space, so we're going to call them vectors. Then h of 1 plus h prime of 1 is equal to p of 1 plus q of 1. That's what h of 1 is, right? H of 1, if you plug in 1 both sides, that's p of 1 plus q of 1. Plus h prime of 1 is, if you differentiate both sides, h prime would be p prime plus q prime. So you're going to end up with p prime of 1 plus q prime of 1 if you evaluate h prime of 1. And then you can just shuffle them around because addition is commutative. I can put p of 1 plus p prime of 1 together plus q of 1 plus q prime of 1 together. Then this will be 0, this will be 0, so you end up with 0 plus 0, which is 0. And this shows that h of x is in U, so we show that it's closed under addition. Okay, so closed under addition. Okay. What's the last step I have to do?
Prove it with vector multiplication. I mean,
Yeah, scalar, yeah. So close under scalar multiplication. So now we go for number 3. If p of x is in U and c is in R, or c is in C, depends on whether your vector space is a real vector space or a complex vector space. Okay. So I'm just going to write or C is in C, just to point out the fact that it really doesn't matter if your scalar field for the vector space is a real field or complex field. Okay. So now what we have is, so px is in U and c is in R. Let h of x now be c times p of x. Okay. Then, since p of 1 plus p prime of 1 is 0, h of 1 plus h prime of 1 equals to c times p of 1 plus c times p prime of 1 equals to c times p of 1 plus p prime of 1, which is just 0, because this is 0. So this proves, sorry for the lack of space here, this is a proof for closed under, this is closed under multiplication. And really scalar multiplication. So we've proved all three things. So 0 is included, it's closed under addition, and closed under vector addition, and closed under scalar multiplication. Yes?
So let's say, like, when we do the first step, that 0 is not included. We stop there, and that it does not exist in the subset, correct?
Oh, wait. If 0 is not included, then it's not a, it's still a subset, but it's not a vector space.
Oh, it's not a vector space.
So for example, if this was 1, well, certainly there are polynomials that would satisfy this, so this is a non-empty subset. But definitely zero, if it's a zero polynomial, this wouldn't be true. So zero is not included, and therefore immediately it's not a subspace.
So we stop there and we don't.
We stop there, and then you don't have to continue. Yeah. If any one of them is shown to be not true, then you just stop there.